Hello everybody, welcome back to a brand new video. In this video, we're going to discuss a problem by the name of North Pole Dawn. So in this video, the Ural Mountains, or the mountain range in Russia, as you may know, it's encircling the North Pole. The radius of the circle is 4 times its own height. So what date will an observer on the North Pole see dawn? And this problem, we're assuming that the Earth is a perfect circle and the observer's height is negligible. If most of you live outside of the Arctic and Antarctic circles, you will see the sun rise and set every day, so it's a bit weird. But for those who live in the Antarctic or in Antarctic circles, you will know that some days there won't be the sun, other days the sun will be there all day long. It's basically because of the horizon of the observer not fitting with the declination of the sun, which changes every day. So how do we solve this problem? Well, first we must draw the diagram. So let's draw the diagram right here. RE is the radius of the Earth. Right here. And this is the observer down the North Pole. And this is the wall. Notice that we will only need to take into effect as one plane because it's a wall and it's encircling him. And so this is the distance between the observer and the wall, this d here. And because this d is on the curvature of the Earth, it causes a small angle of alpha here. So this x here is the distance between the observer and the top of the wall, because if you want to look through a wall, you have to see things that are above the wall relative to you. Because of that, it causes this angle of theta. And notice that we can put theta as this 90 degrees plus delta. Now, what's this 90 degrees for? The angle between the floor and the ceiling or the sky is 90 degrees. So the angle between the floor and when you see directly down is also 90 degrees. So yeah, this is the use of the 90 degrees, and we will be left with this delta. What is this delta? This delta is the minimum declination of the objects that is visible to him because he is on the North Pole. And basically, if you're on the North Pole, you will only be able to see things with a declination of 0 to 90 degrees because your horizon is very, very limited. Alright, so now we know that this d here is equal to a part of the whole circumference of the Earth, 2 pi rp multiplied by alpha divided by 360 degrees. So if we do the math here and we substitute the values here, this alpha is equal to 0.068 degrees. Now what does this alpha, getting this alpha tell us? Well, we can find x through alpha by using the cosine rule. So here is the cosine rule to find x, and we will find x to be 7,804 meters. Now we can also apply this cosine rule on the radius of the Earth plus the height of the mountain, which uses x as a factor and cosine theta as a factor here. So if we were to switch these around, we will find a way to express cosine theta in values that we already know, which is our radius of the Earth, the height of the mountain, and the distance, the shortest distance between the observer and the top of the mountain. Now notice on the diagram there I showed earlier that this theta is equal to delta plus 90 degrees. And we can use the analytical trigonometry for cosine a plus b. And by substituting in the values and by knowing that cos 90 degrees is 0 and sin 90 degrees is 1, we have another way of expressing cosine theta in terms of delta. So we just have to substitute in this one for this one, which is what we're going to do next. Notice that I've already taken out the negative signs here and here. We just need to use the arcsin of this value to find the value of the angle delta, which is 14.019 degrees. Now, what is this delta? It's the minimum declination of the objects that he can see because he's on the North Pole. Or another way to put it is the minimum altitude for the objects to be, but since he's on the North Pole, it's basically the same, which is also the declination of the sun during the dawn, or the day of the dawn. So another way to express the declination of the sun as a function of time would be 23.5 degrees sinus the time multiplied by 360 degrees divided by 365.25, or because there are 365.25 days in a year. So we can see how drastic it really is for observers in those big ranges like the North Pole, South Pole, Arctic, and Antarctic circles. And if we were to switch these numbers around, we will find that the delta t here, the number of days away, it will equal to either 31.157 or 145.467 days from March 21st. Alright, so if we look at these and we find the logical one, so logically speaking, the delta t we're taking is the smaller one. Why is that? Because after March 21st, the sun, we can say, moves north, despite it's because the Earth's revolution. We can say that the sun moves north, so yeah, it must be the smaller one because the observer is on the North Pole. So we just add these to March 21st, and we will find that he will see dawn on April 22nd. Alright, this is all for this video. I hope you enjoyed and you learned something new. Thank you.